Hello everybody, welcome to the second half for week 10. So what we're going to do is just build a little bit on the content of the first of our video lectures, and especially on the ideas of the kernel and image of a group homomorphism. And especially we're going to see how the image of a homomorphism relates to the collection of cosets of the kernel in the domain group, and use that to sort of get at the concept of a quotient group, which will be the content of next week's discussions, and is really kind of the last thing that we're going to talk about in this course. So just to recap a little bit from earlier, supposing that we have a group homomorphism from a group G to a group H, it's called phi. As we saw earlier, the kernel of phi is defined to be the subset of G consisting of those elements whose image under phi is the identity element in H. Okay, and we saw first time round that that subset is not empty, it at least contains the identity element of G. What we're going to see now is that the kernel of group homomorphism is in fact a subgroup of the domain group. So the kernel of phi is a subgroup of G. So the strategy for proving this is exactly the same template as we always have for showing that something is a subgroup of something else. We have to show that the identity element is there, that it's closed under the group operation, and that it contains the inverse of each of its elements in G. So the first part of that's already done. If you haven't looked at the first lecture from this week yet, have a look at it, it's there. We know that the identity element in G has the property that its image under a group homomorphism phi is the identity element in H. And that's really a consequence of the fact that a group homomorphism not only takes elements of G to elements of H, but also does so in a way that preserves, or that takes the group operation of G to the group operation in H. So it takes an element that has a neutral property with respect to the operation in G to one that has a neutral property with respect to the operation in H. Okay, if we take a pair of elements in the kernel of phi, we've got to show that their product in G, their composition in G, belongs to the kernel of phi as well. So to do that, what we must do is apply phi, and I'm using a phi here. Let me insert that. We need to apply phi to the product of, to their product in G. Because phi is a group homomorphism, we know that applying phi to the product of x with y in G is the same as applying phi separately to the elements x and y, and then composing the results in H. So the equation here comes from the fact that phi is a group homomorphism. X is in the kernel of phi. That means that phi of x is the identity element in H. Y is in the kernel of phi. That means that phi of y is the identity element in H. So the image of x star y in G is just the composition of the identity element in H with itself in H, which is the identity in H. And that's exactly what it means to say that the composition x star y in G belongs to the kernel of phi, which enables us to say that the kernel of phi is closed under the operation star G of G. Finally, if we have an element of the kernel of phi, we've got to show that its inverse in G is there as well. So to do that, give ourselves some element x of the kernel of phi. If we look at what happens to phi, if we apply phi to the composition x inverse with x in G, that, of course, is the identity element in G, so its image is the identity element in H. On the other hand, the image of this product in G is the product of their images in H. So phi applied to x inverse star x is the same as phi applied to x inverse star phi of x. But x is in the kernel of phi, so phi of x is the identity element in H. This is because x is in ker phi. And that means that the image under phi of x inverse star x is just the image of x inverse, start with the identity, so it's the image of x inverse, and that tells us that phi of x inverse is the image of the identity element of G, so it is the identity element in H, which is exactly what it means to say that x inverse is in the kernel of phi. So the conclusion there is that the kernel of phi, if phi is a group homomorphism, is a subgroup of G, not just a subset. And of course, if we're in the context, if G is a finite group, so Lagrange's theorem applies, we can use that and comment on the fact that the number of elements in the kernel of phi must be a divisor of the number of elements in G, and there's a complementary divisor whose role we will talk about in this short lecture. Okay, the image of phi, which is the set of images in H of elements of G, is a subgroup of H. I won't go through the proof of that because it's very similar, but you can certainly read it in the lecture notes or indeed write it down for yourself as an exercise. So related to any group homomorphism, we have this pair of subgroups. A subgroup of G consisting of the elements that are mapped by phi to the identity in H, and a subgroup of H consisting of the images under phi of all the elements of G. okay, the kernel and image of a group homomorphism. Okay, so another question, and let me draw a sort of little picture here. So in the language of group homomorphisms, what we can say, we've got a group G, and it's mapped by a homomorphism to a group H. Inside G, we have the kernel of our homomorphism, which I'll write in green. It includes the identity element of G. And it gets mapped, everything in the kernel gets mapped to the identity element in H. So this whole green part sort of gets shrunk down to just the identity element in H. Then the other elements of G that aren't in the kernel of phi don't get mapped by phi to the identity in H. They get mapped somewhere. And the image, the set of images of all the elements of G over in H is some subset of phi of H, which is the image of phi. So it's kind of drawn here in this blue color. So it might be all of this group H, but it might only be part of it. So this blue part represents the image of phi. Okay, so that's sort of the picture of a group homomorphism. You have this kernel consisting of the elements that get mapped to the identity. It's not the empty set. It does include at least the identity element of G. And you have the set of elements of H that are images under phi of the elements of G, and that's the image of phi. Okay, so in some sense then, the image of phi, it's a group. Every element in there comes from an element of G, according to a mechanism that somehow translates the group operation of G to the group operation of H, and in particular the group operation of the image of phi, which is a subgroup of H. So the image of phi, it's some sort of copy of G over in H. Okay. It may not be an exact copy of G, because there can be different elements of G that have the same image over in H. So for example, the kernel of phi could contain more than just the identity element of G, but all the elements of the kernel of phi have the same image over in H, just the identity. So all those elements, which are separate elements of G, kind of get mapped to the same element of the image of phi. But nevertheless, there's some sense in which the image of phi is some sort of shadow of G over in H, some sort of copy of G or partial copy of G that maybe doesn't preserve all the different individual elements of G. It might sort of mush some of them together, but it does preserve as well some kind of image of the group operation in G. So the question here in this slide is, how does the image of phi resemble G? If every element of G gets mapped to a different element of H, then the image of phi is kind of an exact copy of G. And in fact, those two groups are isomorphic in that case. They're essentially sort of the same group, but with elements labeled differently. If there are elements of G, different elements of G that have the same image over in H, then the image of phi won't be a full replica of G, but it'll be some sort of partial copy of G. And that's kind of what we're trying to get at by an example in this slide and by a more kind of general argument in the next one. So the example here is the modulus function from the complex numbers to the real numbers. And this picture is not supposed to look like a kind of target or something like that. It's supposed to look like a picture of the complex plane. This is the complex plane. The horizontal axis, of course, is the real axis. The vertical axis is the imaginary axis. We have 0 here at the intersection of the two axes. We have on the real axis, we have the points 1, 2, 3 labeled -1, -2. On the imaginary axis, we have I and 2I, -I, -2I, and -3I. So this is supposed to be the complex plane. The function that we're talking about is the modulus function from the multiplicative group of complex numbers, of non-zero complex numbers, to the group of positive real numbers under multiplication. And it's the function that takes a complex number z to its modulus, or if you want to write down what it does to z in terms of its real and imaginary parts, the modulus of the complex number x plus iy is the square root of x squared plus y squared. So it's the distance from the number x plus iy in the complex plane to the origin, to the complex number 0. Okay, the assertion is that this is a group homomorphism. What that's saying, of course, is that if we take two complex numbers, z1, z2, that the modulus of the product z1, z2, so if we take the product of z1, z2 and take the modulus of that, that's the same as taking the moduli of z1 and z2 separately, which are positive real numbers, and then multiplying those in the real numbers. That's what it means to say this is a homomorphism from the multiplicative group of non-zero complex numbers to the multiplicative group of positive real numbers. Okay, the kernel of this homomorphism is a set of complex numbers whose modulus is 1. So it's a set of complex numbers which are a distance 1 away from 0 in the complex plane. That's the unit circle in the complex plane. It's labeled by this red circle here in the picture. Okay, and if we ask ourselves, what are the images of all the elements under this modulus homomorphism? They live over there in the positive real numbers. What do they correspond to in the complex plane? Well, two elements of the complex plane, two complex numbers, have the same image under the modulus function if they are the same distance away from 0 in the complex plane. So if they're on the same circle centered at 0. So the picture here is supposed to show some circles centered at 0. The red one is marked deliberately in red to show that it's the kernel of the homomorphism. It's the unit circle. The other circles are concentric with that one. They're also centered at 0. They're not the unit circle. So, for example, here's the circle centered at 2, this outer blue one. Okay, all the elements on that circle represent complex numbers whose modulus is 2. They all have the same image under this group homomorphism. That image is 2. And what they represent in terms of the structure of the group of non-zero complex numbers is this red one here is a subgroup. Okay, if we take two complex numbers of modulus 1, their product has modulus 1 as well. But the circle with radius 2 there is not a subgroup. If you take two complex numbers of modulus 2, their product has modulus 4. It's not on that blue circle anymore. But what that blue circle is, it's a coset of the subgroup determined by the red circle. It's just a set of all complex numbers that are twice something that's on the red circle. Okay, so the red one is a subgroup. It's the kernel of the modulus function. The set of all complex numbers of modulus 1. The blue circles are cosets of this subgroup. Okay, the set of complex numbers of modulus 2 is just what you get by taking this unit circle and multiplying every number there by 2. Same for these ones which have lesser radius than 1. This is like this outer blue one here, on the inner part of the circle. That would be what you get by taking all the complex numbers of modulus 1 and multiplying them all by a half. So every value, every positive real value, which can be the modulus of a complex number, determines some coset of the subgroup, which is this red circle. And those are exactly the various moduli. The image of the modulus homomorphism is the full set of positive real numbers. And every one of those positive real numbers corresponds to exactly one of these concentric circles in the complex plane. The concentric circles, of course, fill up the whole plane. They are the distinct cosets of the unit circle, which is a subgroup of the complex plane. So what we see is that there's exactly one element of the image of phi, which is the set of positive real numbers, corresponding to every coset of the kernel. So somehow the elements of the image, for this example at least, what they correspond to in the group that we started with, the group of non-zero complex numbers under multiplication, is the set of these concentric circles in the complex plane. The real number 1 corresponds to the kernel, which is this red circle, and all the other real numbers, all the other positive real numbers in the image of the modulus function correspond exactly to the various cosets of that unit circle in the complex plane. So we have this correspondence between elements of the image and cosets of the kernel in the domain group. Okay, so the domain group here is the non-zero complex numbers under multiplication. The red unit circle is a subgroup of that. All the cosets of that subgroup are all the blue circles, which fill up the entire complex plane, except for 0. And the elements of the image correspond exactly to those blue circles. They're the possible different moduli of complex numbers. Okay, so that's an example. And if you are thinking about this example, you could think about applying the same logic to the examples that we had in the first round. For example, the logarithm function and the determinant function for 2x2 matrices. The assertion on the next slide is that this is not sort of an accident of this example, that in general, if you have any homomorphism of groups, what elements of the image correspond to are cosets of the kernel. So our picture here would be, maybe we have a pair of groups, G and H. So here's G, I'll draw it as a kind of a rectangle. Here's H. within G, we're going from G to H, we have our homomorphism phi. Within G, we have the kernel of phi, which I'll write in green. And all the elements of the kernel of phi get mapped by phi to the identity element of H. In particular, all the elements in the kernel of phi have the same image under phi. Okay, so supposing we think about taking different elements of G, and bear in mind that the group G, the kernel of phi is a subgroup of G. Okay, so it's got this language going with this kernel of phi, but it's a subgroup of G, and we know a lot about subgroups. We know that a subgroup determines distinct cosets. So corresponding to the kernel of phi, which is a subgroup of G, we've got all these different slices of the group G, which are the distinct cosets of the kernel of phi. They look somehow like that to fill up the whole group G. What we can observe is that if we have two elements of the same coset of the kernel of phi in G, then to differ from each other, one of them is the other one, composed with an element of the kernel. So if you have two elements of the same coset of the kernel, let's say they're called x and y, then y is just x composed with something that's in the kernel. So if you apply phi to x, to both x and y, apply phi to y, you're applying phi to x composed with something in the kernel. The thing in the kernel gets mapped to the identity element in H. So applying phi to x and to x composed with something in the kernel gives the same outcome. So all the elements in this coset of phi also have the same image. All the elements in this coset of phi also have the same image. Okay, here's a little argument that says, if we take a pair of elements, x and y of G, apply phi to both of them, when do we get the same image? Well, there's an equation that says phi of x is equal to phi of y. Well, why does that happen? If that's true, we can compose both sides of this on the left with the image of x inverse under phi. X inverse is an element of G. So just compose both elements here with the image of x inverse. Phi of x inverse composed with phi of x is phi of x inverse x, which is the identity element in G. On the right-hand side, we've got phi applied to x inverse y. So the fact that phi is a group homomorphism says phi of x inverse composed with phi of y is just phi of x inverse y. We can essentially compose the x inverse y inside the parentheses there. This is saying that phi applied to the identity element of G, well, we know that that gives us identity element in H, is equal to phi applied to x inverse y if and only if x and y have the same image under phi. Well, that tells us that phi applied to x inverse y is the identity element in H, which is exactly what it means to say that x inverse y, that element of G, belongs to the kernel of phi. Okay, what are we saying? We're saying that two elements x and y have the same image under phi, if and only if the element x inverse y is in the kernel of phi. X inverse y is in that subgroup of G, the kernel of phi, if and only if y is x composed on the right with something in the kernel of phi. In other words, if and only if y belongs to the left coset of the kernel of phi determined by the element x, which is saying that x and y belong to the same left coset of the kernel of phi. Okay, so two elements of G have the same image under phi if and only if they belong to the same left coset of the kernel of phi in G. That's saying that x and y have different images under phi if and only if they belong to different cosets of the kernel of phi in G. So the elements of the image of phi correspond exactly to the distinct left cosets of the kernel of phi in G. Not only that, but the group operation over in the image of phi respects this division of G into cosets. And what I mean by that is, if we take a pair of elements over here in G, each of them will belong to some coset. We can map them over to H and take their product over in H. That will give us an element in the image of phi. We should get the same outcome if we compose them in G, landing in some coset here, and then map over to H. Okay. So what this gives us is a correspondence between the elements of the image of phi which might be all of H or might not be all of H, and the distinct cosets of the kernel of phi in G. Okay, so every element in the image corresponds to a coset of the kernel over in the original group G. The group operation on the elements of the image then somehow gives us a binary operation on the set of left cosets of G, of the kernel of phi in G, of the subgroup in G. Okay, so somehow this kind of setup gives us a way of composing cosets of the kernel of phi in G. Okay, the elements in the image of phi correspond to distinct cosets of the kernel in G. They can be composed together using the group operation in H, and through the correspondence that gives us sort of a group operation on the set of cosets of the kernel of phi in G. The number of those cosets is the index of the kernel in G. Okay, so this kernel, it's a subgroup of G. If G is finite, then its order is a divisor of the order of G. There's a complementary divisor that goes with it that multiply together to give the full order of G. And what we're saying is there's some sort of subgroup here, or not subgroup, there's some sort of group here whose order is that index, the order of G divided by the order of the kernel of phi, and whose elements are the cosets of the kernel of phi in G. That group is manifested over here as the image of phi. Its elements correspond to distinct cosets of the kernel of phi in G, and it arises whenever you have a homomorphism with a particular kernel. Okay, so what this thing actually corresponds to is something called the quotient group of G modulo the kernel of phi, which can be defined in further contexts than just when you have a group of homomorphism at work. That'll be the content of next week's lecture. But the key point is the image of phi over here, its elements correspond to the cosets of the kernel in the group G. And its operation corresponds to an operation on the cosets, which is somehow consistent with the group operation on G itself in a way that we will revisit next week. The final remark is, we've talked here about left cosets because we're used to talking about left cosets, but the left is in parentheses wherever it appears. And a reason for that is because we can observe that if you take any element x of G, the left coset of the kernel of phi determined by x is the set of all elements in G whose image under phi is just phi of x times the identity element of H. So the left coset of the kernel of phi determined by any element x of G is just the set of those elements of G whose image under phi is the same as the image of x. However, if we were to look at the right instead of the left coset, we could say that the right coset of the kernel of phi determined by the same x is the set consisting of anything that you can get by taking an element of the kernel of phi, composing it on the right with x. If you apply phi to something like that, you get identity element of H composed with x, with phi of x over in H. So the right coset of the kernel of phi, determined by the element x, also is the set of all elements of G whose image under phi is phi of x, the same as the image of x. That tells us that the left and right cosets of the kernel of phi determined by any element of G are the same set. Okay, because both of them can be described as the set of elements of G whose image under phi is phi of x. Okay, so the homomorphism function, it sends all the elements of the kernel itself to the same image, which is the identity element of H. For every coset of the kernel, it sends all the elements there also to the same image. Okay, so this statement that for any x, the left and right cosets of the kernel of phi determined by x are the same set is exactly the statement, which you might recall from the second homework sheet, that kernel of phi, the kernel of a group homomorphism, is a normal subgroup of the group G. Okay, a normal subgroup, remember, is one with the property that every element determines the same left and right cosets of that subgroup. So we're going to come back to this next week and we're going to gather up all these strands and put them together. So for now, it's quite a lot of theoretical elements to digest. So just try to think, if you can, about the idea that what the distinct elements of the image of a homomorphism correspond to are the distinct cosets of the kernel over in the domain group. We're going to pick up all these strands again next week, put them together and define something called the quotient group of a group G modulo any normal subgroup. Okay, but that's for next week. What we have left today is our challenge for week 10. So here's a puzzle for you to think about. If you take any rational number, x, its floor, which is denoted by this kind of notation, is the greatest integer that's less than or equal to x. So if your rational number is 3.2, its floor is 3. If your rational number is 3.5, its floor is 3. So the question is, the puzzle is, or the challenge is, to determine with explanation whether the function which sends every rational number x to its floor, that's a function from the rational numbers to the integers, whether it is a group homomorphism from the group of rational numbers under addition to the group of integers under addition. Okay, so basically what this function does is it just rounds every rational number down to an integer. Okay, so that's one to think about. That's it for today. Thank you very much, everybody, and see you later in the week.